working, right? You weren't there. I definitely was. You said I
Okay. Good morning, everyone. It sounds a little odd, so hang on a minute. Is everybody still able to hear me properly? All right, so we'll continue. Just for today, we'll continue with the chalkboard, and then based upon your answers to the quiz, I'll see what the majority decision is. I'm personally biased towards this because this is how I've been teaching for so many years now. But I'm happy to do the iPad too. Okay? I feel this is how mechanics should be taught on the board. You see the grime and the dust and the dirt. It should remind you of materials breaking. Okay? So, I posted 3 lecture slides on your Carmen page, and on there you will see that I have summarized all the equations that we have derived so far. I'm not going to write them down. You're just going to get cracking on the problem that I have. Okay? The problem. We need to draw the shear force and the bending moment diagrams. And it is implied that when you're doing this, you are finding the support reactions. And I'm probably going to take only one problem and solve it today, but I want to do this very carefully, properly, so that if you know how to solve this problem, you should know how to do shear force and bending moment diagrams. Okay? Alright, here's the problem. I have a simply supported beam. A simply supported beam is a beam with a pin support at one end and a roller at the other. Okay? You have this figure in your handout on carbon. Then I have a distributed loading acting on it. So this is A. B, I have a distributed loading of intensity 100 newtons per meter. This is acting over a span of 2 meters. Then I'm also going to have a couple moment, concentrated couple moment. I acting at this particular location, the magnitude of this being 200 Newton meters. Here are the distances for us. From A to where the beginning of the distributed load is, it's 1 meter. This is 2 meters. Not drawn to scale, of course. Then I have 3 meters, and then I have the remainder is 2 more meters. 3. What I'm not going to do, I'm not going to find the support reactions because I assume that we know how to find it. Okay? So you draw the free body diagram, get rid of the distributed load, replace it by a single equivalent force, sum of moments at a certain point, sum of forces in the y direction. I'll write out all that work when I post the solution of this problem. I'm going to post my solution on top of the notes that one of your peers is kindly consenting to give. Okay? So support reactions you'll end up getting as 175 newtons for A and then 25 newtons for B, both pointing vertically up. Okay, go ahead. This is from statics. Then I need to draw the shear force and bending moment diagrams. So what I'm going to do is on this corner here, or maybe I'll just, if it is fine with everybody, if you have all copied this information down, can I erase this? Yes, take. I'll be marking the forces directly on the body itself. Okay, so that is from statics. Okay, I have AY. B. $25. So shear force then. What are my locations? My locations of interest are where there are loads acting or where there are load changes occurring. Okay, so I start off with X, positive from left to right. Y positive is from bottom to top. This location is 1. X is 0 meters right at the beginning. X is 1 meter right there. X is 3 meters, please notice that. This is 0, this is 1. I come here, X is 3. Then I go from 3 all the way to the end there, which is going to be 6 meters. So this is X is equal to 6 meters, and then the end of the beam, X is 8 meters. And whenever you're drawing the shear force and the bending moment diagrams, you're going to be looking at the left of the X and the right of the X. Okay, so if you're looking at it from the left, then I'm going to call it as X at 0 minus. If I'm looking at it from the right, I'm calling it as X is equal to 0 plus, and likewise for the other disciplines. Okay? Alright, so start with X at 0 minus. This is always going to be starting at 0. Okay, so 0 Newton because there is no beam at 0 minus. Then I go to X is 0 plus, which means this is right after the force AY is acting. So V at X is equal to 0 plus minus the change in the shear. If I have a concentrated force, it's going to see a upward jump if the force is pointing in the vertical direction. Okay, so this is going to be plus 175 newtons. X of 0 minus is 0, so V at X is equal to 0 plus is 175 newtons. first one. This is the second one. Then I keep doing this as I keep on progressing towards the end of the beam. I go to x at 1 minus. Because I see that at 1 meter, I'm going to start the distributed load. So x at 1 minus. Minus the previous step. It's always a change in the shear, except when you're looking at the first point. The first point starts at some ethereal space, where there is nothing going on. Okay? This is b at x is equal to 0 plus, and here is typically what I do. If I see that there are no changes taking place, I just swiftly keep going, and I'll tell you where that comes. This is 0. Between 1 minus and 0 plus, there is nothing going on. So that's one more piece of information I need. Am I making sense to everybody so far? Okay. Go to 1 plus. This is where things get interesting. What should this be?
125.
Some, yeah, keep going, keep going. So, one answer is 175. Was that what I heard? Any other answers? Any takers?
Would the distributed load have an effect on it?
Are we at the distributed load yet?
Yes, because the first arrow of the distributed load is acting at exactly 1, so.
Okay, great. So, if I have to take a distributed load and convert it into a single force, what's that going to be? It's going to be the distributed load intensity times the area under the loading curve. What's the area between 1 minus and 1 plus? 0. Which means that right at the beginning, I don't see the effect of the distributed load playing a role yet. Okay, so this is still 0. So there is continuity there. V at x is equal to 1 plus is still 175 meters. Can everybody see if I write down here, please? People in the back, all the sides and so on. Okay, I'm going to continue in the next line here. And I have made a complaint to the facilities department to get these things running. Hopefully it will run before the semester ends. Maybe on the last day of the semester. Then I do the following. Okay, I see, okay, I have bypassed successfully into the beginning of the distributed load. I go all the way to the end of it, which happens to be at x is equal to 3 minus. V at x is equal to 3 minus V at x is equal to 1 plus. What is this one? You have the handout, some of you may have it open with your iPads. What is the value of this change? It is the area under the distributed loading curve. What is the thing that you've got to be conscious of? What's the direction of the load intensity? It's pointing in the negative y direction, so it has to be the negative area. Okay, so this is going to be minus 100 times 2. Does this make sense to everybody? So, I'm going to skip the algebraic steps, but you've got to be careful. This is minus 200. This is 175. If I bring this on to the right hand side, it's going to be minus 200 plus 175. So the net answer that I'm going to be getting for this guy is minus 25 newtons. I'm going to skip all those steps. Okay, so I'm just going to say V at x is equal to 3 minus minus 25 newtons. And the hope is after this week's homework and next week's homework, You should just be looking at the figure and then drawing the shear force and a bending moment without any calculations. Right? So we're getting there. Then I go from 3 minus to 3 plus. Same idea as between 1 minus and 1 plus. There is no area for the distributed load. The distributed load has stopped anyways, so there is no change in the shear. V x is equal to 3 plus. Is 0. I hope this idea is clear to everybody. Unless and until I have a concentrated force acting, I will not see any change in the shear if I am looking between the left and the right side of a point for a distributed load. Okay? So this tells me x is equal to 3 plus is also 25. Now you've got to start thinking smart. What's my next stop? My next stop is x is equal to 5, 6 minus and 6 plus. Right? That's my next stop. But we looked at the derivations last time and we figured out that this coupled moment does not do anything for my shear force diagram. Which means I can kind of ignore its presence. There's the gorilla in the room, but you can ignore its presence for the time being. And then completely zoom past and go to 8 minus. Does this make sense to you? If you see a couple moment, it's not going to play a role in the shear force diagram. It has played its part in the calculation of the support reactions. It's not like it's not going to do anything to you. It has done its part. It has done its pain to you. When you calculate support reactions, you would have had to include its effect. Okay? So, next step. I'm going to go all the way to 8 minus what's this going to be equal to? Any of the answers?
Positive 20.
Negative 25. So I see 0, positive 25, negative 25. Any other answers? Think. Between 3 plus and 8 minus, where I am stopping short of this concentrated force, is there any force acting? Is there any distributed loading acting? Which means that the change in the shear has to be 0. Okay? So think carefully. Don't be fooled by these concentrated forces. That is why we are doing it in this really painstaking manner. I wouldn't show this work outside to the outside world because you don't want them to see these 8 minus and 3 plus and so on, but this is just to help us understand that there are these discontinuous events taking place at these points where there are forces acting. Then after some time you can discard them at your will, once you are ready with it. Is equal to x at 3 plus, which is minus 25, so this is minus 1. The last step, you've got to come back home. You started from home. The difference between the value of the shear force between 8 plus and 8 minus is equal to whatever you're seeing here, which is acting in the vertically upward direction, so that's a positive 25. If I bring this creature onto the right hand side, that's a negative 25. They cancel each other and you get 0. If you don't get 0, the mistake is made either in your statics, that is the first place I would look for a mistake, or the mistake is made somewhere along your journey to the end of the beam. Okay? So this is plus 25, so V at x is equal to 8 plus is 0. It always starts from 0, ends it. Cannot be any other number. So, in some sense, you can always work backwards if you made a mistake and figure out, okay, it has to start from 0 and end at 0. So, I know that the value of the change in the shear should be something that gives me 0. So, what should be the support reaction at the end? It should be plus 25 newtons. So, that's another way of thinking about it too. Okay. Any questions so far? Is everybody on the same page? Okay, now we will draw the shear force diagram because the bending moment is a little more tricky to draw. I'll draw the shear force diagram and I'll draw it here. Okay. And somewhere here I'm just going to redraw the beam with all its glory. You know the distances. So I'm first going to mark the distances. My shear force in newtons, x in meters. What are my stop points? 0, 1, 3, and 8. In between I also mark this 6 meters because I know that there is something going on which will be useful for the bending moment diagram. So 0, then 1, then 3, 6, and 8. Okay. At 0 I start at 0. That is 0 minus. Between 0 minus and 0 plus there is not a whole lot of space. So when I am drawing 0 plus, I am directly shooting from 0 newtons to 175 newtons straight up. Okay, it is positive 175, so I'm going to go up on the shear force diagram. 175, so this is a line that I join. So far so good, everybody? Okay. Then I have to go from 0 to 1. Between 0 and 1, I see that at 1 minus I'm at 175, at 1 plus also I'm at 175. Between 0 and 1, so this is x is equal to 1. This is x is equal to 3 meters. And this x is equal to 8 meters. In between I have x is equal to 6 meters. Between 0 and 1, I don't see any distributed load, which means that the slope of the shear force diagram, which is the magnitude of the distributed load, is equal to 0. So I'm just going to go as a straight line. Okay? So this is one here. Does this make sense to everybody? So between dV by dx is 0 because there is no load intensity there. Then I see, okay, there is something funny going on at x is equal to 3. It's minus 25, so I first mark minus 25. Okay? I need to be here. I am here. How do I go from here to here? Yes, sir.
You just go straight down and all the way to the right, which is high.
So straight down in the form of a sloped line, straight line. So I'm here. I need to get there. Do I go down, then come here and then travel there, or do I travel as a line that joins those 2 points? So no guessing. Between 0 and 1 and 3 meters, so between 1 and 3, the slope of the shear force diagram is equal to the load intensity value, and there is actually a distributed load. What is the intensity of that load? The intensity of that load is constant. But don't forget the negative sign. The negative sign is because it is pointing downwards. So it is a constant negative slope from 1 to 3 meters. Does this make sense to everybody? It's a constant negative slope. Okay? Which means that I'm actually crossing the zero axis or x-axis at a certain point. I want to find out what that point is. I want to find out what the distance is. So this is 1 meter here. This is 3. This is 6. This is 8. I draw similar triangles. Okay, so I look at, I'm going to call that distance as some z. Everybody still able to see my writing clearly? People in the back and all sides of the room. Okay, so I call that distance as z from here to there, not the entire thing, I'm sorry. I call that amount as z, so the remainder of the distance because the total length of that segment is 2 meters, starting from here all the way to there is 2 meters, so the remainder is going to be 2 minus z. And I make use of similar triangles by saying 175 divided by z, 175 being the height of the triangle, z being the width of the triangle, is equal to 25 by 2 minus z. Notice, I did not call this as minus 25 because I'm trying to find the distance. The distance is a scalar. It's not going to be affected by whether the magnitude of my triangle is minus 25 or not. Should not. Is this point clear to everyone? I can wait here for a minute if there are questions. Here is what I'm trying to do. The shear force is passing the x-axis, crossing the x-axis and going on to the negative side, the dark side. That point there is a point of great interest for me because we know in the back of our mind that the slope of the bending moment diagram is equal to the shear force value. So which means the slope of the bending moment diagram at that point is equal to 0. If the slope of a curve is 0, then it means the curve is either hitting a maximum or a minimum. So I want to find out what exactly that location of crossover is. Okay, so that's called as the point of zero crossing. I solve for that using the idea of similar triangles. I have one triangle here. And then I have the other triangle here. I look at the idea of similar triangles and then I calculate z. So z will be 1.75 meters. This is the point of zero crossing. It is important that you find these points. They may happen more than once in a shear force diagram. We don't know. We've got to find out all events of these things. Okay? Then it's all smooth sailing. Once I go to minus 25, I see that from 3 to 8, it's all minus 25. So just keep going straight. There are no distributed loads. So there is no change in the slope of the shear force diagram. Just to zoom past. And then I know that I have to go home, climb up these steps to a welcome from your parents. Alright, so this is our shear force diagram. That's 1 and 3. Are there any questions, please? Any questions on what we have done so far? Is the shear force diagram clear to everybody? Why am I drawing the line here as a straight line with zero slope? Is because the slope of the shear force diagram is equal to the load intensity value. If there is no load intensity, the slope is zero. If there is load intensity, the slope will be equal to the magnitude of the load intensity, keeping in mind if I have a load intensity pointing down, it is accompanied by a negative sign, which means that it's a negative constant slope. It's a decreasing slope, a constant value. All right. So that being said, we are ready for the bending moment diagram. Okay? Yes, yes.
You just real quick, just go over the direct relationship between the shear diagram and the figure.
And the figure here?
Yes.
Right, so I'm starting here, which is why I'm using this particular value. So that value is marked as a 0 here. Okay? Then I'm going to the next step, which is x at 0 plus. So I'm still at 0. So I'm climbing from here by an amount of 175 newtons. Then I'm going from 175 newtons to x at 1 minus, which is right here. I'm going as a straight line with 0 slope because there is no distributed loading here. Then I realize, okay, look at the end of the distributed loading, that's at x is equal to 3 meters, which is somewhere here, right? Yeah, right there. This is 3 meters. I know that I have to come to 25 negative. How do I go from 175 to 25? Is I look at the slope of the load intensity. That slope is a constant value, but with a negative sign because the load intensity is pointing in the vertical downward direction. So I go down as a straight line, negative slope. Crosses the x-axis at a point, as the point of 0 crossing. If the shear force crosses the x-axis, at that point the bending moment is either local maximum or minimum. I find that point using similar triangles. Then I say, okay, I need to just go to the end of the beam because nothing special is happening in between 3 and 8. I go to 8 minus, it's minus 25. So I'm right here. Then I see I got to go home, climb up. Okay, perfect. We're going to get the bending moment curve. Okay, that's a little more complicated. Yes, question.
Why is it 2 minus z again?
Oh, that's because the total length here is 2 meters, all the way from 1 to 3 meters. So if I call this distance as from here to the point of 0 crossing as z, the remainder of that distance is whatever is the total length minus the z.
Oh, okay, I see now.
All right. So I'm going to erase all of these. Is everybody good to go? Okay. Thank you. Now, word of caution. If you have to draw the bending moment diagram, you need to have the shear force diagram done, and you also need the main loading diagram, the figure that we started off with. You need both these pieces. So I'm going to draw them. You don't need to, you have it already. I'm not going to give it any thickness and so on. So this is AY, BY. I have the distributed load. The thing I'm interested in is there is a concentrated couple moment, so that's a creature that's going to upset the cart. (200 Newton meters), distances.